A video then on types of radiation, the constituents of them, the effect they have on the parent nucleus that emits them, and how to balance nuclear equations. So 3 types of radiation that we concern ourselves with: alpha, beta, and gamma. And you can see there the alpha particle, when it comes out of the nucleus, is a large particle, the beta is a small one, and the gamma is electromagnetic radiation. It's a ray, just energy. And they're called alpha, beta, and gamma after the first 3 letters of the Greek alphabet. So alpha emission then, relative to the other 2, this is an enormous particle. 2 protons and 2 neutrons. It has a mass of something like 8,000 times the mass of a beta particle. So it's a really big particle relative to the other 2. So it has a mass number of 4 because it has 4 particles, 2 protons, 2 neutrons, and an atomic number of 2 because there are 2 protons in those 4 particles. Because it's got 2 protons, it has a double positive charge, +2. So uranium is an alpha emitter. Alpha is emitted by large nuclei because only large nuclei are unstable enough to lose 4 particles from them, 2 protons, 2 neutrons. And so by conservation of mass, if I've got 238 over here, I must have 238 over here. 4 of those are the alpha particle, so that has to be 2, 3, 4. If I've got 92 protons, I have to have a total of 92 over here. So if 2 of them's here, 90 has to be the atomic number of thorium. So thorium then, atomic number of 90, mass number of 2, 3, 4. Another example, radium, another large nucleus, decays by alpha to radon. Radium is 22488. This particular isotope of radium, 224. Radium is always 88. So if it decays by alpha, then the radon that is produced must be 22086. Radon is always 86 because, as you know, the atomic number is what dictates the element. Plutonium decays by alpha to uranium. Notice we had uranium-235 before. This decay of plutonium results in uranium-236, but uranium was always 92, plutonium was always 94. But this is a particular isotope of plutonium producing a particular isotope of uranium. So 236 plus 4 is 240, 92 plus 2 is 94. And thorium decays by alpha to radium. Radium, you can see, decays to radon, as we looked at earlier. Beta emission then, well, alpha was a large particle, 2 protons, 2 neutrons. Here we have a neutron breaking up to form a proton and an electron, and the electron leaves the nucleus, that is the beta particle. So the overall mass of this isn't going to change because you are simply changing a neutron into a proton, so the mass number doesn't change, but you've got 1 more proton than you had before. So here we have an isotope of hydrogen, tritium, decaying by beta to make helium. Carbon, carbon-14, decays by beta to nitrogen. So there is no change in the mass number, as we said before, but there will be 1 more proton here than there was here, and so to make the numbers balance, the atomic number of beta is -1. So 7 minus 1 is 6, 14 plus 0 is 14. Lithium also decays by beta. Lithium 8 decays by beta to beryllium. Same deal. 8 plus 0 gives you 8. 4 plus minus 1 gives you 3. Sodium decays by beta to magnesium. Sodium 24, that is. So 24 plus 0 is 24. 12 minus 1 is 11. Gamma emission then. Well, gamma tends to occur after alpha or beta decay because the nucleus has too much energy after the decay of alpha by beta or alpha, and so that excess energy is emitted to allow the nucleus to become more stable, and it's emitted as a gamma ray. So there is no mass, no rest mass for the gamma ray, and there is no charge. So the issue with ionizing radiation is that when the radiation collides with matter, it ionizes it. So there was alpha coming in and colliding with some atoms and ionizing them, removing electrons, leaving them positively charged. And of course that is damaging to living tissue, and that can do harm to the DNA. It can kill cells. It can cause radiation burns. It can cause cancer because of the damage to the DNA. So the alpha particles do a lot of damage because they are big, heavy particles. They're slow moving in that they're moving at about 1/10 of the speed of light compared to beta, which will move at up to 0.9 of the speed of light. But they are big, heavy particles, do a lot of damage, have a lot of collisions because they're big over a short range, run out of energy and stop. Beta, though, are small, light, fast particles, and so they don't do as much damage, but they do damage over a longer range. They can go further. And one of the ways that we can detect radiation is the use of photographic paper. So if you bring your source up to some photographic paper, and here you've got a couple of barriers, you've got a coin, you've got some card, and the photographic paper wrapped in paper here. When you develop your film, you can see lots of exposure here, less exposure here, and less exposure again in the middle. Gamma isn't very ionizing at all. It has to be absorbed by the nucleus, and most of them are not.